Welcome back. This is our video solution to problem 9 from Superquiz 3. In this problem, we're asked to give an example of a ring where the fundamental theorem of arithmetic fails. So the fundamental theorem of arithmetic is telling you that you can break up an element as a product of primes in a unique way. And we want to go into a ring where even maybe the notion of prime has to change. And so the example that we've been working on in class is where you should start here, and that's with what we're calling the Dedekind integers. So we call this z adjoin root -5, or we've been using Dedekind's notation where we replace root -5 with theta. So this is the ring of Dedekind integers. And we showed that the fundamental theorem of arithmetic just fails, and it fails pretty miserably. So FTOA, that's our abbreviation for fundamental theorem of arithmetic, fails. Now Dedekind was able to recover some version of it by replacing the numbers in z theta with ideals, and that of course we'll get on to later on in the course. But for now, we're just going to stick with the elements. And what this problem is asking us to do is to actually give an example that shows that it fails by showing that you have some number which can be decomposed into indecomposable elements in two different ways. So the canonical example is the number 6, which you can write as 2 times 3, but also as 1 plus theta times 1 minus theta. And we can use an argument, which I'll show what the argument is in a little bit, but we can use an argument to show that each one of these 4, so the 2, the 3, the 1 plus theta, and the 1 minus theta, these are all indecomposable. But this then is two different factorizations. And if you go back to Euclid's lemma, which would say that the way we should characterize primes is if they divide a product, then they divide one of the factors. Here we have 2 divide 6, which is equal to 1 plus theta times 1 minus theta. And 2 does not divide either 1 plus theta or 1 minus theta. So 2 in this case, while it's an indecomposable element, it fails the Euclid's lemma version of being prime. So we're not going to be able to decompose 6 as a product of primes at all in this case. And even if you say, okay, fine, well, let's not require them to be primes, let's require them just to be indecomposable, you can decompose it into indecomposable, that's not a problem, but you lose uniqueness. Well, let me give you a different example, one that we didn't use in class. So in this example, I'm going to try to avoid using any integers whatsoever. So here I've used a 2 and a 3. I want to use just Dedekind integers. So we're going to look at -1 plus 2 theta times its conjugate, -1 minus 2 theta. So what I claim is that this is going to equal the same thing as if I multiply 4 plus theta times its conjugate, 4 minus theta. Now, because I'm multiplying conjugates, I'm just going to be getting the norm. And the norm in this case I get by taking the square of the components and multiplying the second component, right, after I square it, by 5. So in this case, I would get -1 squared plus 2 squared times 5. Okay, so let's see, 5 times 4 is 20, plus 1 is 21. And over here, I'll have 4 squared plus 1 squared times 5, which is going to be 16 plus 5, also 21. So I have two different products, both equal to the same number, 21, so they're equal to each other. And so if I can show that these are indecomposable elements, then we'll know that that we have a counterexample to the fundamental theorem of arithmetic in this ring. So how do we show that they're indecomposable? So what we'll do is we'll show it for one of them, and the proof for all the rest will be identical. So let's just take the first one on the left here, -1 plus 2 theta. What I'm going to do is write down the norm of it. So the norm of -1 plus 2 theta. We know that this is equal to 21, right? We just computed it. So if I could decompose -1 plus 2 theta, so assume -1 plus 2 theta is equal to a product, say a W times Z, where W and Z are Dedekind integers. Well, now I can apply the norm map to this equation. I'll have 21 is equal to the norm of -1 plus 2 theta. And that will equal the norm of WZ. And by the product of norms theorem, this will be the norm of W times the norm of Z. Now, if I'm trying to break this up in a way where not one of them is a unit, right? That's not helpful, right? To show something is decomposable, they need to be not units. So let's assume they're Dedekind integers, but they're not units. Then I know that their norms are not 1. Okay, so this here implies that the norm of W and the norm of Z are not equal to 1. Okay, well now I have the number 21, and I want to write it as a product of positive integers, neither of which is a 1. So my only hope is 3 times 7. So this implies that n of W, n of Z as a pair is equal to 3, 7, or 7, 3. Okay, it doesn't matter which one. Well, let's write down what the norm of, say, W is. So if W is equal to A plus B theta, then the norm of W is equal to A squared plus 5B squared. And is it possible for such a norm, such a number, A squared plus 5B squared, to equal 3 or 7? And I claim the answer is no. In fact, once we show that it can't be 3, well, it won't matter whether it could be 7 because we need one of these to be 3, right? So let's try showing that this is not equal to 3. Well, first, this 5 is really going to mess things up, right? So if B is at least 1, then B squared is at least 1, and then 5B squared is at least 5, which would imply that A squared plus 5B squared, 5B squared, is at least 5, which is strictly greater than 3. So if we want this to equal 3, then we're going to need for B to be equal to 0. Okay, so thus, if 3 is equal to n of W, which is A squared plus 5B squared, then B equals 0. But that tells you that 3 is equal to A squared, which is not possible. 3 is not a perfect square. Okay, so 3 is not a perfect square. Thus, n of W does not equal 3. All right, and similarly, it wouldn't equal 7, right? You got to work a little bit harder, but again, we don't need to actually show that because we need one of these to be 3. So n of W can't be 3, and for the exact same reason, of course, n of Z can't be 3. Therefore, we cannot write -1 plus 2 theta as a product where neither of them is a unit. Okay, hence, -1 plus 2 theta is indecomposable. And you'll notice the only thing we used in this argument was that the norm is 21, not anything specific about -1 plus 2 theta other than its norm. All right, so similarly, -1 minus 2 theta, 4 minus theta, 4 plus theta are also indecomposable.